Welcome, students. We are going to discuss about series solutions near an ordinary point. Before I introduce what are ordinary points, let's work through an example and see how this goes. So the idea is you are given a differential equation y prime minus 2xy equals to 0. And you want to find a solution for this. So now this is a toy example. So I can solve it directly as well. Note that this equation is separable. I can write it as dy by y equals to 2x dx. And if I integrate on both sides, this gives me integration of dy over y equals to integration of 2x over dx, 2x dx. And this gives me ln of absolute value of y equals to x squared plus c, and then when you bring y on the other side, so you get y equals to e to the power x squared times e to the power c with a plus or minus sign, of course, but you can observe that in the following. We can observe that as a e to the power x squared. So this is your solution. But now what we're going to do is we are going to run an experiment with a series solution, okay? So before I go there, normally we do not do this. Normally, we would not use series solutions. If we can find the exact solution, right? So if we could find exact solution, right? So let's look at this simple problem and see the whole process. So assume y of x, your solution is a form summation n equals to 0 to infinity an x to the power n, and where an is to be determined. Yeah. All right. So now let's see. So we have y0 is clearly a0, right? And so on and so forth. So now let's find out what is y prime. So what is y prime of x? So y prime of x is summation n equals to 1 to infinity n times an x to the power n minus 1. Now let's take this and substitute in this equation here. So we get, so we have y prime, which is, let's call this 2 sub 2 in given equation. So we get y prime, which is summation n equals to 1 to infinity n an x to the n minus 1 minus x 2xy, so 2 times x summation n equals to 0 to infinity an x to the power n equals to 0. So now what we'll do is we'll try to get the coefficients together as a power of, and then power of xn. So this starts with n equals to 1. This starts with n equals to 0. So first let's move this inside. So we get summation n equals to 1 to infinity n an x to the n minus 1 minus summation n equals to 0 to infinity a n x to the power n plus 1. Now, if I want to combine these, I have to combine them power by power, right? So this is equal to 0. So then let's break this guy now. So it's starting from n equals to 1. So we are going to rearrange this thing so that the powers match. So how are we going to do that is the following. So we can break it as, say, let's take the first element out. So we have first, when n is 1, what do we get? N is 1. For this guy, we get a1 plus summation n equals to 2 to infinity n a n x to the power n minus 1 minus summation n equals to 0 to infinity 2 an x to the n plus 1 equals to 0. Now, why am I doing that? I'm going to basically make these powers. So I want to basically have this is n equals to 0. I want the same thing here. So I will do the following. We can write this as now. So this same series can be written as a1 for the first part. We can write this as summation n equals to 0. So, or you can write it as I equals to 0, where I is equal to n minus 2. So what do we get in that case? We get I equals to n minus 2. So in that case, we'll get, so n will become, so this becomes I plus 2 equals to n. So we'll have I plus 2. an is, well, I plus 2. The power will become I plus 1 minus summation n equals to 0 to infinity 2an to the n plus 1. Now I is basically a counter like n, so I can replace that by n. So I have a1 summation n equals to 0 to infinity n plus 2 a n plus 2 x to the power n plus 1 minus summation n equals to 0 to infinity 2an x to the n plus 1 equals to 0. Now I could have done this directly, but we just saw how to shift the indices here. So now this would give us a1 plus, now we can combine them together. The reason is the powers are equal. We could have combined them otherwise as well, right away, but then we had to be more careful about the coefficients. So we get summation n equals to 0 to infinity n plus 2 times a n plus 2 minus 2an, the whole power x to the n plus 1 equals to 0. Now this being 0 is same as saying this is same as 0 x to the power n, right? So you're comparing the coefficients then. So if you compare the coefficient, you will see that coefficient of a1 is 0. So a1 coefficient is 0. Not only that, you'll get n plus 2 times an2 minus 2an is 0. So in this case, so this is what we get. Now we want to work it out. So now we want to basically find out all the AIs, right? I mean, after all, finding a solution is finding AIs because x to the n is known, right? So we need to find out AIs. So the AIs are the coefficient to be determined. So let's work with odd coefficient first. So a1 is 0, right? That's what we got here. A1 is 0. And from here, we can see, if you compare this, you get an plus 2 is 2an divided by n plus 2. So now this would mean, so after A1, so next we can find using this as A3 is 2A1 upon 1 plus 2, which is also going to be 0, right? A5 is 2 upon n plus 2 times A3, that's going to be 0 as well. Yeah. In fact, you can prove that, so we have A, so you can prove that an plus 2 is basically, so an is 0. So continuing this, you can prove that an is 0 if n is odd. Now let's proceed with the even ones. So what is our a0? A0 is y of 0. That is not known to us, right? Because, well, we found out a1 to be 0. We don't know what a naught is. So that will be specified to us by initial conditions. Now, what is when n equals to 0? A2 is, when you put in this equation, we have an plus 2 equals to an 2 upon n plus 2 times an, right? So a2 is going to be 2 upon n plus 1 times a n plus 2 times a0, which is going to be y naught times divided by 2 by, so 2 plus 2, which is going to be y naught divided by 2. When n equals to, so this was n equals to 0. When n is 2, we get a4 equals to 2a2 divided by 4, which is y0 by 2. So when n is 4, n is 2, we get a4 is 2a2. Okay. Now when n is 4, we see that a6 is going to be 2a2, so 2a2, sorry, 2a4 divided by 6, which is going to be y0 times 2 times 3, right? So when n is 6, you get a of what? You get a of 6 plus 2, right? Which is a of 8 equals to 2a6 divided by 8, which is going to be y0, 2, 3, and 2 by 8 is going to be 4. So this implies, you can prove actually, that a to the power 2k is going to be y0 by k factorial, k greater than or equal to 0. Yeah, so you can prove, you to have a rigorous proof can be done using induction. Using induction. So therefore, the full solution is all odd coefficients are 0. And all even coefficients are a to the power 2k is same as a8 was what? A8 was y0 by, so a8 was y0 by 4 factorial. A6 was y0 by 3 factorial. A4 was y0 by 2 factorial. So is a of 2k is y0 by k factorial. So now let's put it back in the, so yx is summation k equals to 0 to infinity a to the power 2k x to the power 2k. Why is that? Because all the odd ones are 0, so we just need to write the even ones. So this is going to be summation k equals to 0 to infinity y0 by k factorial x to the power 2k, which is y0 common summation k equals to 0 to infinity x to the power 2k over k factorial. And if you recall, this is basically y0. This is a formula for e to the power x squared. So therefore, y of x equals to y0 e to the power x squared. And this solution and the direct solution are in agreement, right? So this is how we go about using power series to find out the solution. The above method can be extended without changes to a higher order differential equations as well. Now, it is for higher order differential equation that the method achieves the potential, since many important functions arise as solution to such equations, for which there is no exact formulas in terms of elementary functions. All right. So this method makes more sense in the higher order differential equations. All right. So let's deal with second order differential equation. So you are starting with y double prime plus px y prime plus qx y equals to 0, where p of x and q of x are special functions. They are basically functions which are analytic at point x naught. So what does it mean by being analytic at x naught? So take px, then px can be written as a power series an x minus x naught to the power n, and px converges for all x minus x naught less than rho for some rho. Yeah. So being an ordinary means that it is, so basically a point being ordinary means that you have, they satisfy the following. Similarly, qx, so qx and px both converge. So qx also comes with its own power series. So qx and converge for all x minus x naught less than some rho, or some rho greater than 0, then we call such a point as ordinary point for the equation. Okay. Otherwise, such a point will be called a singular point. Okay. So ordinary point is defined for the equation, for the differential equation. Namely, if you take this differential equation, I'm repeating again, that p of x and q of x have some power series. So q of x also has some power series. And the idea is that px and qx converge for some x minus x naught less than rho, then we call such a point as an ordinary point for the equation. The points which are not ordinary will be called singular points. So let's have the following theorem for the solution. So suppose we have y1 and y2 are the solution to this equation. Px y double prime plus qx y prime plus rx equals to 0, with initial conditions y1 x naught is 1, y prime x naught equals to 0, y2 x naught equals to 0, and y2 prime x naught equals to 1, then such a solution forms a fundamental set. So let's try to compare. So here there was no px and here there's a px. So what is the difference in this case? So in this theorem, we'll consider a special kind of analytic function. So let's consider px and qx and r of x to be polynomials. And you want, if you convert it in this format, then what you want is that the denominator should not become 0. So all we need is that p of x naught is not 0. Yeah. So these are polynomials and we have p of x naught is non-zero. In that case, we'll get an ordinary point, right? It would imply that x naught is the ordinary point for this equation. So this should be given here. So please add these conditions. So now we want to basically see whether they will form a fundamental set. So we have y1 prime. So these are the solutions. And we want to check whether it will form the fundamental set or not. Okay, so let's proceed on that. So we have the following. So what is Wronskian of y1 and y2 at x equals to x naught is basically W of determinant of y1, y1 prime, x naught at x naught. We are computing the Wronskian at x naught. So y1, y1 prime, y2, y2 prime at x naught, x naught. So we get that is y1 x naught is 1, y1 prime x naught is 0, y2 x naught is 0, this is 1, and so this determinant is 1. So since Wronskian is non-zero, this implies y1 and y2 form a fundamental set of solution. So note that all you need is Wronskian to be non-zero at one point, right? Because we have Abel's theorem which connects. So Wronskian was Wronskian naught times some exponential. And this, if it is non-zero once, it's going to be non-zero throughout. So that's why it's enough to check at one point. Okay. All right, so now let's start with, so we are moving back and forth in the sense that here we have p of x and q of x are analytic function. Then we restricted the case to a polynomial. So the reason for doing that is because we understand about polynomials. Now, suppose we have x naught is an ordinary point for the differential equation. Yes. So that means what? So we have that px and qx are analytical at x naught. Then for any number y naught and y1, there is a power series solution such that y double prime plus pxy prime plus qxy equals to 0, with y of x naught equals to y naught and y prime x naught equals to y1. So this theorem is telling us that if you take an ordinary point, there is a solution to the initial value problem, right? Now, our solution is given in terms of power series. So we are interested in basically what will be the radius of convergence, right? So the radius of convergence of the solution about x naught is at least large as the minimum of radii of convergence of two power series P and Q of x naught. So why is that? So what does it mean? It means, first of all, radius of convergence of P is P of x is, say, R1, and radius of convergence of Q of x. Now, first of all, I'll write them as a series, copying them from above. We wrote that these are the series, right? X minus x naught, x minus x naught to the power n, and so radius of convergence of Px be R1 equals to R1, and this is equal to R2. Then radius of convergence of a solution, of y of x is at least is greater than equal to minimum of R1, R2. Yeah, so this is happening around x naught. So again, the philosophy is that the coefficients Px and Qx determine to a huge extent how the radius of convergence of the solution is going to be. And that is not surprising, right? So now let's work on this. Y double prime minus xy equals to 0. And let's find a general solution to this. So this is what is called as Airy equation. So here, what is our P of x? So if we compare with P of x, y double prime plus q of x, y prime plus r of x, y equals to 0, we'll see that what is P of x? P of x is 1, q of x is 0, r of x equals to minus x. Now, where are we finding the solution? So we need to find solution around x naught, but note that P of x naught is not 0 for all x belonging to R, x not belonging to R. So therefore, every point x not belonging to R is ordinary. Okay. Again, I could have written this as dividing, I could have thought about it as Px plus Qx with the coefficient of this to be 1 by dividing by coefficient of 1 throughout. So coefficient y double prime, which is 1 again. We could have thought about this as this equation as well. And in that case, we have Px is 0, that is analytic throughout. Qx is 0, that is analytic throughout as well. Okay. So now we want to basically find a solution to this. Okay. So assume y equals to summation n equals to 0 to infinity an x minus x naught to the power n, where x naught is any fixed is fixed. Now note that instead of working with x naught, we'll work with x. So we'll consider, for simplicity, take x naught to be 0 to illustrate the point. So we have y of x summation n equals to 0 to infinity an x to the power n. Now we need to basically take the derivatives and substitute in this equation here. So this implies y prime of x is summation n equals to 0, sorry, starting from 1 then, because you took the derivative, n a n x to the power n minus 1, and y double prime is going to be summation n equals to 2 to infinity n into n minus 1 times a n x to the power n minus 2. Now substitute in the dE. So what dE? Y double prime minus xy equals to 0. So therefore we get summation n equals to 2 to infinity n into n minus 1 a n x to the power n minus 2 minus x y, which is summation n equals to 0 to infinity a n x to the n equals to 0. So now I'll basically equate it. So we want to equate the powers. So this is going to be summation n equals to 2 to infinity n into n minus 1 a n x to the power n minus 2 minus summation n equals to 0 to infinity a n into x to the power n plus 1. So now we want to basically make the powers equal. So let's start on that. So first of all, what I'm going to do is look at the first term. So we have here the first term is going to be 2a2 plus summation n equals to 3 to infinity n into n minus 1 a n x to the power n minus 2 summation n equals to 0 a n x to the n plus 1 equals to 0. So I'll bring this up to the and the way I'll do that is the following. Again, let I be n minus 3. So what do I get? This becomes 2a2 plus summation I going from 0 to infinity. So n is going to be what? I plus so we get n plus 3. So we get, so I becomes what? N becomes I plus 3 times I plus 2 times a of, now instead of an I will have I plus 3, and here it will become I plus 1 minus summation n equals to 0 to infinity a n x to the power n plus 1, so 0. So from here we can get that a2 must be 0. And if you compare, you can substitute n equals to, instead of I you can write n, so you will see that this implies n plus 3 times n plus 2 times a of n plus 3 minus a n equals to 0. So this gives us a of n plus 3 equals to a n upon n plus 3 times n plus 2. So let's see. So we get what? So we get a0. So from here we'll get what? This means a0 So this means what? So from here you can see that A0, if you take A0, determines. So from A0 you'll get A3. From A3 you'll get A3 plus 3 6 dot dot dot. That is, so A0 determines A3, A6, so on and so forth. And we get what? So A0 determines this guy, or it determines A3K, right? For n equals to 1, 4, 7, and so on. Right? Because if you look at A0, you'll get A0, you'll get A3, and so on and so forth, right? So now let's look at A1. A1 determines, so A1 determines A4, consequently A7, so on and so forth, or A of 3K plus 1. Similarly, A2 determines A5, A8, A11, and so on. All right, so let's see. So we get the following. So what do we get? We get A3 equals to A0, because A0 is not known to us, right? So this will be decided by initial condition, right? So is the initial condition given to us? No. So A0 will be determined by the initial condition. So we get A3 equals to A0 divided by 3 times 2. A6 is A3 divided by 5 times 6, which is going to be A0, 2, 3, 5, 6. And similarly, A9 is going to be A6 divided by 8 times 9, which is going to be A0 times, so these will be 2, 3, 5, 6, and then 8, 9. So you can see that there are gaps here, right? There's a gap here, there's a gap here so there's a gap of 4, and then there's a gap of what? There's a gap of 7. So you can decide then A3n, so therefore A3n is going to be A0 times 2, 3, then 4, 5, sorry, 2, 3, 5, 6, then 7 is missing, then 8, 9, dot, 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 you are going to n, so it's going to be 3n minus 1, 3n. So this is your A3n. So similarly, you can see A4. So now we'll talk about, so let's talk about now A4. So A4 is going to be, what about A4? A4 is going to be A1 divided by 3 times 4. A5, so 4, what is the next one then? The next one is another plus 3. So A7 is A4 divided by 6, 7, which is going to be A1 divided by 3, 4, 6, 7. You see there is a gap here of 5. So if you continue this, you will see that A of 3n plus 1 is going to be A1 divided by 3, 4, 6, 7, dot, 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 3, n 3n plus 1. Of course, n greater than equal to 1 here. N greater than equal to 1. Now comes the one which is determined by, so we have A2. So now let's see what is determined by A2. So in that case, so we know A2 is 0, right? So if A2 is 0, that means A5, which is A2 upon, A5 is A2 upon 2 plus, so A5 is going to be, so 2 plus 3 and 2 plus 2. So 2 plus 3 times 2 plus 2, which is going to be 0. So similarly, A8, A of 3k plus 2 is 0 for all k greater than equal to 1. So now, therefore, y of x can be seen as what? So what solutions survive? So what are the solutions we have? We have this guy, and we have this one here. So we have y of x is going to be a0, 1 plus x squared by 2 times 3 plus x to the 6 divided by 2 times 3 times 5 times 6 dot 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 x to the power 3n. I'm going to represent a general element here. So 2, 3 dot 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 3n minus 1, 3n plus, or let's write plus here, plus a1 times x plus x to the 4 by 3 times 4 plus x squared times 3 times 4 times 6 times 7 dot dot dot. So this should also keep on going, dot 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 x to the power 3n plus 1 divided by 3 times 4 dot 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 3n times 3n plus 1, and this process keeps on repeating. So this is how the solution looks like. So we have solved the following equation. Okay. So this equation is Airy's equation. Now look at the solution for, so this, so claim this solution converges for all x. Why? Because our theorem guarantees it, right? That what is the radius of convergence of, so here if you look at this radius of convergence of, if you compare with px and qx, px is 0 and qx is of, qx equals to x is infinity, and radius of convergence of p of x, so is sorry, qx is minus x is equals to 0 is infinity. So the radius of convergence of your solution is going to be infinity. So it converges for all x. Yeah, this is because of the almost factorial in the denominator. Yeah, you can check it, can check by root test. By actually by ratio test, not by root test. Yeah, the root test is going to be painful here. Now we can plot the function by terminating. So this is a plot of the function by terminating it after some time. So this is when n is 3, you get, this is your solution. Yeah, when n is greater than equal to 6, So these are some of the solutions plotted. So when n is greater than, so when n is 6, this is how the solution looks like. When n is 12, this is how your solution is. Yeah. So on. So if you look at this, these are the numbers and corresponding to the solution. Corresponding solutions are drawn. So what do these numbers mean? These numbers are where you're truncating this series, right? So if you truncate the series, you will get a polynomial. And of course, that polynomial will have sufficient number of roots, and then it will follow the following. However, the actual solution is given here. So y1 is given here with this, right? So note that it may seem less satisfying than the actual closed form, but realistically, this is what happens with the realistic scenario, right? Because the solution sometimes may not exist in terms of elementary antiderivatives, right? So or in terms of elementary functions. So thank you for your attention.